All right, hey folks, Emily here. In this video, you are going to learn how to pre-train your own foundation models on SageMaker. So let's jump in. All right, so what's going on here? So the case is you want to pre-train your own foundation model. Now, why would you want to do this? Now, of course, you might be an AI startup who's out to build the next foundation model. And so obviously in that case, you're gonna wanna build your own. But also when you pre-train foundation models, it gives you the ability to unlock performance in new areas. So if it's on new data sets, new domains, new parts of knowledge that aren't already contained in pre-trained foundation models, then in that case, pre-training your own foundation model is a way that you can apply neural nets to terabytes of data to train the neural net on that terabyte of data, and then apply that in use cases that are relevant to you. And so that's the workflow that we're going to understand in the video here today. And so first off, on SageMaker, we provide ephemeral training clusters that you can use to spin up these machines and to interact with these accelerators. When you're pre-training your own foundation model, this can be anywhere from hundreds to thousands of accelerators, and no one wants to provision and rack and stack and maintain all of those accelerators. And so the cloud is a natural choice for training foundation models. And then in SageMaker, we've been investing in distributed training libraries, GPU performance, and overall orchestration for your cluster for many, many years. And so you get to use that through an API call. And that's what we're going to understand here today. And so when you're creating a training cluster in SageMaker, what's happening is essentially you're creating this training job API call. So you're invoking an API to create a training job. When you happen, of course, it's going to hit the SageMaker control plane. And then SageMaker is going to spin up and provision these resources for you. So that can be CPU-based machines, that can be GPU, either large or small, in many different instance types and sizes. You can use custom accelerators like our Trainium instances, which is what we're going to look at here today. And then in your SageMaker training job, essentially we're tracking all of that cluster for you and keeping it healthy and aligned. And then we're going to invoke your script on that set. So your data sets, of course, you can provide those in your S3 buckets. You can also set up an EFS volume or FSX for Lustre, which is an optimized distributed file system that actually scales to the number of mounts. So as you increase the number of nodes that are trying to read data, FSX for Lustre will increase the overall bandwidth for that volume in order to keep the performance high. So you can mount a Lustre file store, and then you're going to create your training image in ECR. And then you can use a base AWS deep learning container and then just add your training code on top of that. And so SageMaker downloads that training image for you. And then we also set up a log stream out to CloudWatch. So essentially, once the instances and the image have been initialized, then we'll start streaming the logs to CloudWatch, and you can view all of the action as it's happening. We'll store the metadata and we'll store the hyperparameters in the SageMaker control plane, both in the console and in Studio, so that you can view all of the activity and then again, hold on to the assets and the artifacts as you're experimenting. Once the job is finished, we'll send the output model, such as the model checkpoints, to your storage volume. And then the core training loop itself, again, really is the job of distributed training. So including model parallel and data parallel techniques in order to shard your model over all of the accelerators as necessary, and then keep the distributed gradient descent running online. And of course, you can do this with your own deep learning models. And so in this view, we're using the SageMaker Python SDK. And then this PyTorch object here, again, is a object that's pointing to so it's a wrapper around the training job API. So you're calling PyTorch and then estimator.fit, and that's invoking that training job API. It's also pointing to the deep learning container. So this is pointing to the base PyTorch container for SageMaker that AWS keeps alive for you and updates. So as there are major changes to PyTorch, the framework, we'll update our base container so you can use those. And then you'll point to the framework version you want to use, the Python version, and then you'll define the instance right here. So the number of machines you want to use, the type of those, bring all of your own custom hyperparameters right here, bring your metric definitions, and then again, you're going to call model.fit. And then we have many different modes for passing data to that training cluster. One easy way to get started is an S3 path. So if you have a smaller data set, then you can just load that from S3 directly. And so this mode, the default is just going to copy that file or that directory onto your training job, and then start to copy after that, start to train once you've copied it. So really not too much data. And then once you do larger sets, then you can start to stream using the fast file mode. So that's an option. And then again, if you're working with terabytes, then just FSX for Lustre is a really stable option. So now let's take a look at a demo. And so in this demo, you're going to pre-train your own 70 billion parameter Llama 2 model on SageMaker. We're going to use Trainium machines. And so we'll open up a notebook in SageMaker Studio. We're going to use warm pools for SageMaker training, so you can reuse those machines, and that helps us write our training scripts. Then we'll interact with the distributed training libraries to execute the training loop, and then ultimately profile and troubleshoot the job. So let's take a look. Okay, so now we're going to take a look at a demo of pre-training our own Llama 2 70B. And so here we are in SageMaker Studio. And so again, within SageMaker Studio, we're going to open up Jupyter Lab. One thing to note, you can add, of course, multiple spaces here in Jupyter Lab. And then with each of these spaces, this is where you change the instance type. So you just click on the name of the space, and then you can stop it. You can open Jupyter Lab here. And then once it's stopped, you can set different instances. So if you want to just run on a GPU or run on an accelerator or maybe even a multi-GPU machine, you can do that right here. Fortunately, I already have it open, so we'll open that. And then the script we're going to use is available publicly. So this is the example notebook that we're using. So again, you're training Llama 2 70B. This is in the SageMaker Trainium examples, so feel free to follow along with me. All right, so we're going to pip install Boto 3. So that happens here. And then we're going to install the Transformers SDK from Hugging Face, the datasets, and then the S3 integration path for that. So this notebook is going to download the wiki corpus, and the model artifact is Llama 2. And when you download that from Hugging Face directly, you need to pass in your token. And so I obviously hid that here, but note that you'll need your Hugging Face token here. So we're going to import the datasets library from Hugging Face, and then we're pointing to this wiki corpus dataset. And so we have the wiki corpus dataset, and then remember the tokenizer comes with each model. So every model has its own tokenizer, and so we need the tokenizer for Llama 2 70B, and that's right here. And then we load the datasets, and we load the tokenizer. And then that happens here. So we've got those loaded, and then next, again, this notebook actually is going to tokenize this data set locally. So we're going to download this data set and then tokenize it on this machine, which is why actually I picked a C5. I think I picked a C5.18, C5.12. Yeah, so a C5.12, which gives you a little bit more compute power, so you can tokenize this rapidly. When you're working with a larger data set, then you could add, actually you could add the SageMaker remote decorator to take this block of code and actually run that on a dedicated machine. So the remote decorator is a way to wrap a single function and then actually spin that up on its own host, which is a nice way for tokenizing data sets. So that's something you could do right there. All right, and so this is grouping the texts and then tokenizing them. All right, and then again, I did this ahead of time. All right, and then I'm gonna point to my session bucket. So this one is of course Llama on SageMaker. And then, so in the notebook again, we'll do the tokenizing locally, and then we just pass it up to the S3 bucket. And so that is here. It says save to disk, but it's actually saving directly to the S3 bucket, which is handy. All right, so that is now in my S3 bucket. After this, I'm gonna run this training job using, again, Train1N. So this is custom accelerators from Amazon, and we are going to use 8 of these machines. So 8 overall nodes, and then each node has 32 processes per node. A couple of the other hyperparameters here. So the global batch size, that is the total batch, so the total number of records we're gonna hold in memory for this entire 8-node cluster. And then the sequence length, which we essentially take from the model, so that's 4096. And then your pipeline parallel degree. So the pipeline parallel degree essentially is the way that we're going to split the different layers in the neural network. So your Llama 2 model, of course, is a decoder-based transformer model. Each transformer head can be quite large, and so we need to place the different blocks in your neural network on different accelerators. And so that's what the pipeline parallel degree indicates, is essentially how we're taking the heads in the Llama model and then placing different layers on different accelerators. The tensor parallel degree is another piece here. So tensor parallelism is where you're gonna take one block or one attention head, and that head might be just so large that it doesn't even fit on a single accelerator by itself. And so the tensor parallel degree is still placing that object on accelerators, but here we're placing one head on the 8 accelerators. So just one attention block over all of those 8 cores. And then the data parallel size is the total number of accelerators that you need to host essentially a version of the model. And so that's how large your data parallel size, that's your data parallel size. Okay, and then we have the batch size per model replica. And so that is so we have the global batch size, which again, we saw at the top, and then the batch size per model replica, essentially that is for each of those model partitions. That's how many like objects from the data set they are going to have. So batch size per model replica. And that is your micro batches. Arun, thank you for the notebook. Love it. Let's keep going. Okay. So we're gonna set more hyperparameters here. So your train batch size, training directory, maximum steps, sequence length. Then all of these we're just passing to this hyperparameters object. You can pass anything you want to the hyperparameters object. What's happening here is that in the training script that you're gonna use to invoke this, you wanna build in arguments basically that capture this. So when you add a new hyperparameter here, just add it as an argument to that training script that we'll use to invoke your job. And then you'll be able to use those from inside the script. And we're gonna take a look at that in this demo here. All right, and then, so optml refers to a piece inside of the training container. So that's within the training image. Most of the program will run inside of optml, so that's here. And then this is the, again, fully managed deep learning container. So it's the AWS DLC, and this is a global DLC. So you're gonna point to that account everywhere in the world, and then just change out your different regions. and change out the image that you want to use. So let's just take a look at this. Deep learning container. Yeah, there we go. So these are the deep learning containers. And so again, they're updated very regularly, and you can view some of the available images and the SageMaker images right here. Oops, clicked on the wrong button there. There we go. Great. So these are all of the available deep learning containers. And then the SageMaker ones are down below. Alternatively, you have the ones for sort of EC2, EKS, ECS. And then essentially you need to pick the right image based on what framework you're using. So PyTorch, TensorFlow, Hugging Face. And then if you're doing training or inference, and then if you're on a CPU, GPU, or a Trainium, or an Inferentia neuron core. And then this is the example URL. So that's your image. And then you just update this based on whichever region you are running this in. And so that is exactly this, basically. It's the PyTorch training image for Neuron, and then it's 1.13. All right, and so we'll pass in a job name here. And so the checkpoints, when you are training on an S3 bucket with data coming out of S3, then you can write your checkpoints to S3 directly. If you're using FSX for Lustre, then actually you're gonna write the checkpoints to Lustre, and then Lustre will replicate that out to S3 after you're done. Okay, so we'll point to the checkpoints in S3. So again, we're gonna write the checkpoints during the training job, and then those will show in S3 on completion. Many environment variables to set here. So EFA, nickel, neuron, malloc, XLA, all sorts of environment variables here. And then here are quite a few flags to look at. So this is telling neuron the type of model you're using, which is a transformer, your distribution strategy, this is LLM training, and then enabling this infinity saturation, and then setting a cache directory. All right, so then we set the PyTorch estimator. So I'm gonna show you this script. So we have this local run llama with the neuron distributed script right here. This is the instance type, so 32XL. And then we're passing that Docker image, and we have 8 instances. We're passing all of the hyperparameters, role, job name, environment variable, fast file mode, because we're pointing to S3. And then this is where we do the warm pooling, basically. So you need to add permissions for warm pool resources. So it's another service limit increase. It should be automatic if you already have access to those instances. It should go through very, very quickly. And so essentially, once you've enabled this, then when you run this job, that cluster will stay warm. Actually, the resources will stay available to you. The image will stay there as well. And then you can rapidly iterate. And so you can run another job using that same base image, but just modifying the script. And then essentially you can test and develop in seconds. And so when you're developing for the SageMaker training API, definitely strongly recommend using this warm pool. And then S3 checkpoints, and then the distribution mode. So this is enabling torch run. All right, so let's check out that training script. So that's over here in scripts. All right, so quite a few objects here. Obviously, you have a requirements.txt. When you pass this, SageMaker training will look in your source directory, which we pass here. So we're telling it to look in this directory. And then within this directory, it will default to looking for a requirements.txt. If it finds one, it will just do a pip install. If you have packages that aren't pip installable, then you want to extend that deep learning container. So this image that we looked at above, you can basically extend this Docker image. So you can build a new Docker file, extend this image, add any other packages you need, deploy that to ECR, and then you can use it for your training jobs. Or you can just run it via pip install if it's a Python package. All right, so here is our run llama. All right, so again, we're using the Neuron distributed SDK, which is right here. And that's helping us work with the Neuron machine. So we're getting the data parallel ranks, the data parallel size, tensor parallel rank, and then initializing model parallelism. So quite a few objects here again from Neuron distributed. So parallel layers, optimizers, utils, and then the llama config is coming from Hugging Face. So that's the transformers. And then we're importing quite a few objects from the rest of this repository. And so that's all here. All right, so then I'm not going to go through this in too much detail, but please feel free to study this on your own. So here's this all reduce, which I love. And then the save on the checkpoints. Saving checkpoints is non-trivial in distributed training, particularly for model and data parallelism, because you need to ensure that you're reconstructing the model such that you only have one version of the model and you have a coherent number of components to that. All right, and then this is the core train. And so like most distributed training libraries, it's gonna look to see which rank the script is operating on at that point in time. And basically when it's the leader rank or 0, then in this case, just printing the arguments. We're setting the seeds and then initializing the model parallelism degree, getting the data parallel rank, tensor parallel rank. Then we load the llama config, initialize the weights, and then create the model directly on the host device. And then here is the Neuron distributed, which takes that llama model and then reconstructs it essentially for Neuron. Then we load the model weights, set up the 0 optimizer, and so on. So I'll leave the rest of this for you to study at home, but definitely really interesting. And so when you call model.fit, that does indeed train a model. So it launches these instances, launches this cluster. And then, so here's an example when I trained this with, again, 8 Train-1N machines with 32 XL. And then all of the metadata, the content, the logs are all stored and searchable and versioned by default. So it's really easy to take a look at these, modify previous experiments, and then use that to indicate the rest of your work. So with that, let me show you some resources. Okay, so let's check this out. So the first resource for you is, of course, the distributed training documentation. So this does a good job of walking through some of the key concepts, vocabulary, the APIs, some of the top questions, and all of the other topics that you need to know to get distributed training running. And then, of course, here's your example notebook. So using the Llama 2 70B pre-training with SageMaker Trainium. And then if you'd like to watch my reInvent session on the topic, feel free to check that out from 2023. So with that, thank you. That's a wrap. I'll see you next time.